I'm Jamie Santos, a PhD student in the Autonomous Agents and Distributed Intelligence Laboratory at Oregon State University. Today, I'll be giving an overview of our work, Entropy-Augmented Multi-Objective Policy Optimization in Multi-Agent Systems. This is a method of encouraging behavioral diversity in multi-objective evolutionary algorithms. First, let's take a look at an interesting limitation of multi-objective evolutionary algorithms. In this first example, we have a team of rovers tasked with investigating points of interest, or POIs, in a constrained amount of time. Some POIs are higher value than others. Here, the team of rovers investigates all of the lower value POIs, but doesn't reach the further higher value POI. In the second instance, one rover investigates the lower value POI, while another sacrifices the immediate low value reward for a delayed higher value reward. At this point, the example on the right has a lower realized value, but retains an opportunity that the example on the left has abandoned. If we evaluate these teams only based on their realized reward, the solution on the left may appear preferable, but the solution on the right has preserved an option that could lead to a better outcome in the future. Selection only evaluates what has already been achieved, and therefore has no reason to preserve the behavior that is pursuing that unrealized opportunity. This illustrates the broader problem we are interested in. Two solutions can have similar or even identical objective performance while presenting very different opportunities for what they can achieve next. This limitation is especially apparent in the tie-breaking step of multi-objective evolutionary algorithms. This figure comes from the original NSJA2 paper, where NSJA2 is a well-established and popular MOEA. Each solution is plotted according to their fitnesses across all dimensions or objectives, and then ranked according to how many solutions they outperform. To break ties in the final tier of the next generation of the population, points with the lower crowding distance in the fitness space are selected. SPIA2 is another similar MOEA. However, rather than using crowding distance to break ties, it uses k nearest neighbor density. But notice what happens when solutions have very similar fitnesses. These methods have little information about which solution is actually more valuable to preserve. In that case, selection may effectively come down to an arbitrary choice between solutions that are equivalent from the perspective of the objectives. When breaking ties of solutions with similar fitnesses, random selection is used. This means that two solutions can have essentially the same objective performance, but represent very different behaviors, and the optimization process has no mechanism for recognizing the difference. One of those solutions may be discarded simply because it happened not to be selected during tie-breaking. More recently, quality diversity methods, such as multi-objective map elites, have demonstrated the utility of incorporating behavioral information into the selection process of solutions. In multi-objective map elites, Pareto fronts are maintained over a grid of designer-specified behavioral descriptors. This method effectively tiles objective space within behavioral space. However, at its root, it still shares the underlying limitation of random selection within niches, as each Pareto front is evolved according to standard MOEA practices. Furthermore, this method now introduces another layer of complexity. When selecting a solution, the user must not only determine how they value different objectives, but also the utility of one behavioral niche over another. This leads us to our research gap. Can we leverage behavioral information in MOEA selection directly? Concretely, from this we can obtain two things. We would be able to reuse existing infrastructure with minimal modifications, including decision-making methods. And, more importantly, we could get performance gains from currently unused information that is already present in most problem formulations. To understand how we can actually incorporate behavioral information into the selection process, let's take a look at another rover example, say we have the same setup as before, with a team of rovers tasked with visiting different POIs. This time, one rover explores and then claims a low-value POI. The second rover simply doesn't move. This results in just one low-value POI being claimed. Now, say in another instance, one rover similarly claims one low-value POI, and the other heads toward the high-value POI. It ultimately achieves the same reward as the first example, but its behavior is more likely to achieve a higher value POI. Despite the same rewards, we see that the first example has a lower joint trajectory entropy, and that the second example has a higher joint trajectory entropy. This leads us to the core insight. We can encode behavioral information and include it in the fitness evaluation. In practice, this means adding the behavioral metric, in this case, the joint trajectory entropy, scaled by a hyperparameter, beta, to the fitness value used in selection. Now you might be thinking, so how do we find beta? And in this case, optimal beta values were found experimentally via an incremental sweep. So, shown is an example of the hypervolume over NSJ2 generations for a preliminary experiment, only varying beta. For simplicity, the results from the best beta value will be reported in the following experiments. So here's experiment 1. We performed 2 experiments to see how incorporating joint trajectory entropy into the fitness function affects the ultimate fitness of the Pareto front. In the first experiment, we positioned a small team of 2 rovers near a set of low-value points of interest. And we placed a barrier in front of a second set of higher-value rewards. Each POI corresponds to one of 2 objectives, say, a different kind of resource. The experiment was arranged such that globally optimal strategies must find the other side of the wall, and trade-offs emerge from determining how much time to spend at each objective. The top image illustrates an example of greedy behavior in simulation, and the bottom is an example of the team sacrificing quick, local rewards for delayed higher rewards. In 30 runs, we see that the average hypervolume beneath the Pareto front was higher when incorporating the entropy bonus than when not. A beta value of 0.05 was selected via standard hyperparameter tuning procedures. However, due to the large difference in rewards between the high-value POIs and the low-value POIs, the variance of the results remains high even after 30 trials. More trials are necessary to make conclusions regarding statistical significance. However, this variance can also serve as an indicator for at what generation solutions discovering the higher-value POIs were introduced to the population. In the earlier generations, we can see that the results using entropy contain solutions in its population that found the other side of the wall earlier than the results that did not include entropy. In the second experiment, the trade-offs are solely temporal. We again begin with a small team of 2 agents tasked with visiting points of interest. They are surrounded by low-value POIs nearby and higher-value POIs further on. Here, the objectives are the total reward of the first half of the episode and the total reward of the second half of the episode. This top image illustrates an example of the team prioritizing the low-value POIs early on and then moving on to the higher-value POIs, which in this case resulted in higher rewards for the first half of the episode and lower for the second half. The bottom image is an example of the team quickly moving through the lower value POIs and spending more time getting to the higher value POIs, which resulted in lower rewards for the first half and higher rewards for the second half. Here are the results for the temporal trade-off experiment. With 10 seeds, we see no significant difference between using entropy and not using entropy in the final NSJ2 generation. This suggests, at least in this environment, that entropy may be a less useful measure of behavioral diversity for improving sequential diversity, that is, preserving solutions that defer their behavior over time. Please note that this result is different than what was shown in the paper as it includes more samples. Upon evaluation of the number of unique solutions in the Pareto front, we noted that occasionally the number decreased when using entropy than without. This highlights one limitation of the method. On the left is an example of a simplified set of solutions mapped to their fitnesses across objectives. We can see that several solutions map to single points and interpret these groupings as families or clusters with similar objective performance. When applying the scaled entropy values, we introduce separation between overlapping points, giving greater value to solutions with higher joint trajectory entropies. However, if the scaling factor is too large, a single solution can then dominate an entire family of otherwise competitive solutions along the Pareto front. In other words, adding entropy can actually reduce the number of solutions that survive preservation. Rather than using entropy to distinguish between solutions, we can end up using it to eliminate groups of solutions altogether. Ultimately, this can result in a less diverse Pareto front and therefore hypervolume beneath the Pareto curve. So here's what we've learned. From the experiments, we saw that entropy was likely more suitable for task 1 than task 2. This suggests that there isn't necessarily a single behavioral descriptor that will be useful across all tasks. Therefore, we likely need to carefully consider not just how we incorporate behavioral information into selection, but also what sort of behavioral information is useful to the specific task at hand. We also noted that Pareto diversity is sensitive to the scaling factor used. If the behavioral information is weighted too heavily, it can overwhelm the original objective information and cause otherwise competitive solutions to be discarded. One way to combat this would be to instead use a lexicographic selection strategy, where behavioral information is only used to choose among solutions within the same fitness cluster rather than being allowed to change the overall Pareto ordering. So, while these experiments reveal some limitations, they also suggest that behavioral information could provide a useful additional signal for preserving solutions if we are careful about what information we use and how we incorporate it. From these lessons, future work will investigate other behavioral measurements. Examples include state space coverage, action entropy, or k nearest neighbors distance to other solutions in behavior space. Another interesting direction would be to vary the degree that behavioral measurements are used in selection, similar to the idea of temperature cooling that already exists in evolutionary algorithms. Finally, in this work, we defaulted to applying the behavioral bonus equally across objective fitnesses. However, in reality, this may not be the case if the objectives themselves are asymmetrical or different dimensions. Finally, here are the key takeaways. Current implementations of MOVAs evaluate solutions in objective space and can therefore discard behaviorally distinct solutions with similar objective performance. Entropy is a promising behavioral metric for preserving exploratory team behaviors when spatial exploration and dispersion are useful. However, behavioral utility differs for different tasks, which motivates further investigation of team-level descriptors. So, the broader takeaway isn't that entropy is universally the right descriptor. Rather, these results suggest that behavioral information can provide an additional dimension along which we can preserve solutions, but we need to understand which behavioral information is actually meaningful for a given task. And now here are the citations we used for this presentation. Thank you for listening. Please email us with any further questions you may have.